Hi guys, Dr. Colbreth here with an example problem from chapter 16. Here we have an ideal gas process on a PV diagram and some questions about it. We're given one value explicitly, that the number of moles is 0.02 moles, and the rest we're going to have to get off of this chart. And it asks us here three questions. What are the initial and final temperatures? What kind of process is this? And what are some of the other ways to get from the initial to the final state? So first of all, just looking at the shape, we can identify that, or we suspect at least that this is the shape for an isothermal process, and we can verify that in part one here, where we check the initial and final temperatures. So we're going to use PV equals nRT, and we have two states that we're going to consider: the start and the end state. So P1 V1 equals N times R times T1. Or T1 is equal to P1 V1 over N times R. Plugging in some values, we get that T1 is equal to P1. Looking at our chart here, we see that that's 2 atmospheres, so we need to convert to SI units, so this is going to be 2 times 101,300 pascals times V1, which is 300 cubic centimeters, or 300 times 10 to the minus 6 cubic meters, divided by the number of moles, which is 0.02 moles, divided by the ideal gas constant in SI units, that's 8.314 joules per mole Kelvin. Plugging this into our calculator, we calculate the temperature at state 1 is going to be 366 Kelvin. And now we can repeat this process at the ending state. We're going to get that P2 times V2 is equal to nRT2, or T2 is equal to P2V2 divided by N times R, which is going to be the pressure at point 2, which from the chart we read as 6 atmospheres. So this is going to be 6 times 101,300 pascals times the volume, 100 cubic centimeters from the chart, so 100 times 10 to the minus 6 cubic meters, divided by the number of moles, 0.02 moles, times the ideal gas constant is 8.314 joules per mole Kelvin. So we do verify that in fact this is 366 Kelvin, and so this shape, as we suspected, is in fact a isothermal process, meaning the temperature does not change if we vary the pressure and volume and follow this curve on the PV diagram. Now, it isn't worth noting that we don't have to follow this path. We could take a straight line path, or we could, have an isobaric process followed by an isochoric process and get from the start to the end point. And in that case, the temperature would not remain the same the entire time. The temperature would decrease through the isobaric process and then increase again through the isochoric process. Alright guys, so that's just one quick example of using the ideal gas law in chapter 16.